For trial 1, we measured both the normal force and the frictional force acting on the object as it moved across the surface. The normal force was recorded to be approximately negative 7.85 newtons, which represents the force pressing the object against the surface, while the frictional force we measured was about negative 4.75 newtons. The negative sign simply indicates that the frictional force is acting in the opposite direction of motion, which is expected. To determine the coefficient of friction, we use the standard formula, which is the magnitude of the frictional force divided by the normal force. So we took the absolute value of 4.75 newtons and divided it by 7.85 newtons. When we do this calculation, we get a coefficient of friction of approximately 0.61. This value tells us how much resistance there is in between the two surfaces in contact. A coefficient of friction of 0.61 is relatively high, which suggests that the surfaces are fairly rough or that there is a strong interaction between them. Because of this, more force is required to move the object across the surface. It's also important to consider possible sources of error in this trial. For example, there could have been slight inconsistencies in how the force was applied, or the surface may not have been perfectly uniform. Additionally, any small delays in measurement or human reaction time could have affected the recorded values. Overall, trial 1 provided a reasonable and consistent value for the coefficient of friction, and it helps us better understand how the materials interact when motion occurs.
Good evening, my name is Jade Saucedo, and this is Physics Force News. On tonight's segment, the foundation of friction. Tonight we're going into the world of mechanical resistance. Our objective today is to peel back the curtain on why things move, or don't. We've noticed in past experiments that theoretical values rarely match reality because of one constant invisible force: friction. Friction is more than just a nuance. It's a property of the interaction between two materials. Our mission is to calculate the coefficient of friction, a unitless number that tells us exactly how sticky or slippery a surface interaction is. We are looking for two specific values: the static coefficient, which governs objects at rest, and the kinetic coefficient, which applies once motion has begun. To do this, we've gathered our materials: a mass-loaded cart, a flat testing track, a high-precision force sensor. The setup is straightforward but requires precision. We are using the flat surface method. By pulling our object with a force sensor, we can measure the exact newtons required to break the bond of static friction and maintain a constant velocity. Mathematically, we are anchored by Newton's law. When an object is on a flat surface and we pull it at a constant velocity, the pulling force P is equal to the friction force F. By definition, F equals mu N. On a flat surface, the normal force N is just the object's weight, or mg. Therefore, our golden formula for today is mu equals P over mg. Stay tuned as we go to the lab floor and begin trial 1.
Hey guys, this is Alexa Melendez. I am going to be talking about lab number 9. So for lab number 9, what we were working on was grabbing the friction from the elements that prevent us from achieving theoretical values with exactitude. So it is based on the friction and the qualities of both of the materials. So once they come together, we are supposed to be getting the connect, which is at least one object moving, the coefficient of the static friction, which was greater than the coefficient of the kinetic friction. So we basically are collecting data to allow us to determine the friction of the coefficients. So for example, I was supposed to work on the trial number 2, which is going to be right down here. The numbers that we got for trial number 2 were negative 4.85, and we got negative 4.00, which was the steady region. As you can see here, it's just pretty much, I grabbed information from the lab activity, so I could have everything here. The formulas that we were using, pretty much just reviewing that information. And these, for trial number 2, I'm so sorry, it's just the values of the static and kinetic coefficient of friction. As you can see in these images, these are the 4 different trials that we did. I can't really zoom in closely into it right now, but pretty much it's just running the trial to compare the numbers and to see how different they come out each time that we ran the trial. For example, here is just showing you how it accelerates, how the velocity changes. Down here is just how it goes faster. Here is just a constant. Here it was mostly constant, and then it would just accelerate fast. So it's just pretty much reviewing the information that we grabbed from the day that we worked on the lab. I want to say thank you for my teammates. That day I was unfortunately not able to go into the actual lab, but I was provided the information so I could talk about it and mention it for this part of the video. So that's pretty much it for me. I appreciate your time. And like I said, my name is Alexa Melendez. Thank you.
Good evening. My name is Jade Salcedo, and you are watching Physics Force News. On tonight's segment, the outlier factor, Trial 3. In our final run, Trial 3, we see the true nature of experimental science. As our teammates begin the pull, the force climbs significantly higher than in our previous 2 runs, hitting a massive peak of 8.51 newtons before the cart finally budges. To understand this outlier, we have to look at the math step by step using the formulas provided in our activity outline. First, we established our normal force. On a flat surface, the normal force is the weight of the cart, calculated as mass times gravity, or more commonly for us, mg. Assuming our standard lab mass of 1 kg, our denominator is 9.8 newtons. Next, we solve for the static coefficient mu s. We take that peak pull force of 8.51 newtons and divide it by our weight of 9.8 newtons. This gives us a unitless static coefficient of approximately 0.868. Once our cart overcomes that initial stickiness and moves at a constant velocity, our sensors show the force settling at 5 newtons. Following the same procedure for the kinetic coefficient, mu k. The math, we divide our kinetic force of 5 newtons by our constant weight of 9.8 newtons. This results in a unitless kinetic coefficient of 0.510. What we are seeing here numerically is a perfect demonstration of the physics we discussed earlier. The force required to start motion is significantly higher than the force required to maintain it. Despite the higher raw numbers in this trial, the mathematical relationship between static and kinetic friction remains consistent as we move towards our final averages. Once again, my name is Jade Salcedo, and that is all for tonight's segment in Trial 3. We will be moving on to our final averages.